let's say I have something moving with a constant velocity of 5 meters per second, and we're just assuming it's moving to the right, just to give us a direction, because this is a vector quantity, so it's moving in that direction right over there. And let me plot its velocity against time. So this is my velocity. So I'm actually going to only plot the magnitude of the velocity, and you could specify that like this. So this is the magnitude of the velocity. And then on this axis, I am going to plot time. So we have a constant velocity of 5 meters per second. So its magnitude is 5 meters per second. 5 meters per second. And it's constant. It's not changing. As the seconds tick away, the velocity does not change. So it's just moving 5, it's just at 5 meters per second. Now, my question to you is, how far does this thing travel after 5 seconds? So after 5 seconds, so this is 1 second, 2 second, 3 second, 4 second, 5 seconds right over here. So how far did this thing travel after 5 seconds? Well, we could think about it two ways. One, we know that velocity is equal to displacement over change in time. And displacement is just change in position over change. So this is change in position over change in time. Or another way to think about it, if you multiply both sides by change in time, you get velocity times change in time is equal to displacement. So what was the displacement over here? Well, I know what the velocity is. It's 5 meters per second. I know it's 5 meters per second. That's the velocity. Let me color code this. That is the velocity. And we know what the change in time here. It is 5 seconds. It is 5 seconds. And so you get the seconds cancel out with the seconds. You get 5 times 5, 25 meters is equal to 25 meters. And that's pretty straightforward. But the slightly more interesting thing is that's exactly the area under this rectangle right over here. That is exactly this area right over here. And what I'm going to show you in this video, that is in general, if you plot velocity, the magnitude of velocity, so you could say speed versus time, or let me just stay with the magnitude of the velocity versus time, the area under that curve is going to be the distance traveled, or the displacement, because displacement is just the velocity times the change in time. So it's just, if you just take out a rectangle right over there. So let me draw a slightly different one where the velocity is changing. And so let me draw a situation where you have a constant acceleration. The acceleration over here is going to be 1 meter per second per second. So 1 meter per second squared. And let me draw the same type of graph, although it's going to look a little different now. So this is my velocity axis. Give myself a little bit more space. So this is my velocity axis. So I'm just going to draw the magnitude of the velocity. And this right over here is my time axis. So this is time. And let me mark some stuff off here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the magnitude of velocity is going to be measured in meters per second. And the time is going to be measured in seconds. Time is going to be measured in seconds. So what's going to happen here, assuming that we start with, so my initial velocity, or I could say the magnitude of my initial velocity, so just this, my initial speed, you could say, this is just a fancy way of saying my initial speed is 0. So my initial speed is 0. So after 1 second, what's going to happen? After 1 second, I'm going 1 meter per second faster. So now I'm going 1 meter per second. After 2 seconds, what's happened? Well, now I'm going another meter per second faster than that. After another second, if I go forward in time, if change in time is 1 second, then I'm going a second faster than that. And if you remember the idea of slope from your Algebra 1 class, that's exactly what the acceleration is in this diagram right over here. The acceleration, we know that acceleration is equal to change in velocity over change in time. Over here, change in time is along the x-axis. So this right over here is a change in time. And this right over here is a change in velocity. So in this when we plot velocity, or the magnitude of velocity relative to time, the slope of that line is the acceleration. And since we're assuming the acceleration is constant, we have a constant slope. So we have just a line here. We don't have a curve. Now what I want to do is think about a situation. Let's say that we accelerate at 1 meter per second squared, and we do it for so the change in time is going to be 5 seconds. And my question to you is, how far have we traveled? Which is a slightly more interesting question than what we've been asking so far. So we start off with an initial velocity of 0. And then for 5 seconds, we accelerate at 1 meter per second squared. So 1, 2, 3, 4, 5. So this is where we go. This is where we are. So after 5 seconds, we know our velocity. Our velocity is now 5 meters per second. 5 meters per second. But how far have we traveled? So we could think about it a little bit visually. We could say, look, we could try to draw rectangles over here. We were at maybe right over here, we had a velocity of 1 meter per second. So if I say 1 meter per second times a second, that'll give me a little bit of distance. And then the next one, I have a little bit more of distance. Calculate it the same way. And I could keep drawing these rectangles here. But then you're like, wait, those rectangles are missing there, because I wasn't, for the whole second, I wasn't only going 1 meter per second. I kept accelerating. So actually, I should maybe split up the rectangles. I could split up the rectangles even more. So maybe I go every half second. So on this half second, I was going at this velocity, and I go at that velocity for a half second. Velocity times the time will give me the displacement. And then I do it for the next half second. Same exact idea here. Give me the displacement. So on and so forth. But I think what you see is you're getting is the more accurate, the smaller the rectangles you try to make here, the closer you're going to get to the area under this curve. The area under this curve. And just like the situation here, this area under the curve is going to be the distance. Traveled. The distance traveled. And lucky for us, this is just going to be a triangle. And we know how to figure out the area for a triangle. So the area of a triangle is, area of a triangle is equal to 1/2 times base times height, which hopefully makes sense to you, because if you just multiply base times height, you get the area for the entire rectangle, and the triangle is exactly half of that. So the distance traveled in this situation, the distance traveled, or I should say the displacement, just because we want to make sure we're focused on vectors, the displacement here is going to be, or I should say the magnitude of the displacement maybe, which is the same thing as the distance, is going to be 1/2 times the base, which is 5 seconds, times the height, which is 5 meters per second, times 5 meters. Let me do that in that other color. 5 meters per second. 5 meters per second. The seconds cancel out with the seconds, and we're left with 1/2 times 5 meters. So it's 1/2 times 25, which is equal to 12.5 meters. And so there's an interesting thing here. Well, one, there's a couple of interesting things. Hopefully you realize that if you're plotting velocity versus time, the area under the curve, given a certain amount of time, tells you how far you have traveled. The other interesting thing is the slope of the curve tells you your acceleration. What's the slope over here? Well, where it's completely flat. And that's because the velocity isn't changing. So in this situation, we have a constant acceleration. The magnitude of that acceleration is exactly 0. Our velocity is not changing. Here we have an acceleration of 1 meter per second squared. And that's why the slope of this line right over here is 1. The other interesting thing is even if you have constant acceleration, you can still figure out the distance by just taking the area under the curve like this. So we were able to figure out that we were able to get 12.5 meters. The last thing I want to introduce you to, actually, let me just do it until the next video, and I'll introduce you to the idea of average velocity. Now that we feel comfortable with the idea that the distance you traveled is the area under the velocity versus time curve.